Welcome to another episode of the Gradient Podcast, where we interview various people who research, build, use, or think about AI, including academics, engineers, artists, entrepreneurs, and more. I am your host, Daniel Bashir, and in this episode, I am very excited to be interviewing Preetum Nakkiran. Preetum is a research scientist at Apple, a visiting researcher at UCSD, and part of the NSF Simons collaboration on the theoretical foundations of deep learning. He completed his PhD at Harvard, where he co founded the ML Foundations Group. Preetum's research focuses on building conceptual tools for understanding learning systems. In fact, you may have heard about the deep double descent paper that came out of OpenAI a few years ago. Preetum was actually the first author on this paper and has done a lot to benefit deep learning theory since then. This was a really great conversation. We touched on some of the main topics that came up in his thesis about an empirical theory of deep learning, and went into some more interesting topics, his thoughts on the ML and theoretical computer science communities, and more. Hope you enjoy the episode. Preetum, the first question we usually like to start with our guests is how you got interested in AI. So if we could start there, that would be really great.
Yeah, definitely. It's kind of an interesting story because I had two encounters with AI and ML, and the first one didn't stick, and the second one sort of did. So I first started getting interested in ML in undergrad. This was at Berkeley around 2012 to 2014. And mostly I was first exposed to it because a lot of my friends were getting into ML and getting into deep learning. I actually never took any ML class in undergrad or in grad school or ever since then.
Wow.
But so, I picked it up along the way. But a lot of my friends were getting into deep learning then, and I was sort of getting interested. At the time, I think Berkeley didn't have a deep learning class when I started undergrad, but by my senior year, they were spinning that up. It was I had like a math EE background, so I first approached that from the optimization angle, like the convex optimization angle, and the math there seemed interesting. The first real exposure I had to deep learning, at least, was. But I'm going to answer your question with respect to deep learning, not ML more generally. First real exposure I had was an internship I did at Google in 2014 on the speech recognition team. So we were working on the networks that would detect OK Google when you said that. I was working on it was a research team, and I was working on model compression, so like compressing those models down to run on the phone's DSP. And that was pretty interesting. Okay, so clearly something interesting was going on. Like even back then, like something interesting was going on. I'd like to try to understand it. I tried getting into the area back then, but it didn't like aesthetically suit me very well. As in back then, I really liked kind of simple, clean, elegant ideas that I could understand. And ML, like deep learning at the time, was just way too messy for me. Like there were just people were like throwing random things around. Nobody really had a good sense of what was working. It also didn't seem like there was much. So my background in undergrad, I was coming from like the most theoretical side. So I did sort of EE research and TCS research in undergrad. That was more the aesthetic that I was in at the time. And ML just seemed way too messy. Like I didn't even think it would be possible to understand it, and there weren't a lot of people at the time who were trying to understand it. It seemed like a lot of people were like building applications in whatever way, and it seemed like very hacky. And I just kind of had to I like felt like I needed some distance. It wasn't the area for me. So I started grad school in theory. I was doing sort of TCS. It was really interesting for a while. But somewhere in the middle of grad school, I realized kind of that my current research wasn't really like deeply motivating me. I mean, it was very interesting. I was learning a lot of things. I was missing some kind of deeper motivation. So I spent a while in grad school, like around 6 months of exploring different areas, seeing what kind of things are worth working on and that I'm interested in working on. And ML was always one of these things in the back of my mind, like, okay, this is very messy. Someone should figure it out. Like, it's too messy for me, but like, it really should be done by now. And even in grad school, no, this was 2019 or so. I remember thinking, okay, like, we still haven't figured this out. Maybe there's something
Mhm.
that can be done. And also at this time, there were more theorists who were getting into understanding deep learning. I think that was nice for me just to see evidence that people did care about understanding it, and that people were making some partial progress towards understanding it. So okay, maybe now is the time. Maybe like something actually can be done here. And then
Mhm.
yeah, and also once I started, refreshing myself on the literature and seeing what's being done, there were a lot of natural things that, like, natural experiments that I wanted to see done that just no one had done before. That just seemed very basic, like very basic things that we didn't know that it would be easy to know just by doing some simple experiments. And so yeah, I started working in this, and then I was very lucky to have both an advisor that supported me and also like a really good group of students that were also interested in doing this at the same time. And yeah, then sort of things developed from there. Yeah, basically, yeah. So there's like always this lingering feeling, okay, like someone should really be, like, we should have figured it out by now. And then once I started thinking about it, there were like very natural things to try that were just easy, like, hadn't been done, and we should, So yeah, I think there
Mhm.
were a lot of other aspects of this. I like the style of okay, so the style of research was also very much suited for things that I liked. Like I liked sort of some aspects of both theoretical reasoning, but also getting my hands dirty once in a while, and like I just doing the experiment. Yeah,
Mhm.
so there are a lot of different aspects to that. But that's sort of a summary.
That's a really interesting journey. And I guess what sticks out to me is how this also is sort of borne out in the progress of deep learning itself over that period of time. So you mentioned that you were first exposed around 2012 to 2014, which is, I think, pretty close to the ImageNet, AlexNet moment. And so there it's like, wow, these techniques that were developed quite a while back can now actually achieve really great performance on tasks like image recognition. And then over the time where maybe these ideas are brewing before you eventually get into it, we see the dominance of convnets. Eventually, we start seeing transformers. And of course, as you said, the theoretical ideas were still very messy. We had these nice intuitions of things like the bias variance trade off. We had statistical learning theory. And then a lot of papers came and showed, okay, this doesn't really work well. I think a couple that stick out to me, for example, were that Zhang et al. Paper. I think that was 2016, right? Where they found that that these deep networks were basically able to memorize random noise. And so a lot of the really general ideas that we'd formed about machine learning just didn't apply in this regime. So I can see how over time there's definitely more work in that domain. And as you said, there seemed to be a lot of low hanging fruit. One thing I actually did want to touch on though, before we get more into this, is you mentioned that some of your theoretical computer science work in grad school was not motivating to you. And I imagine that probably a number of our readers and listeners are also pretty interested in research themselves or actively doing research. So I was wondering if you could maybe comment on what about that research didn't motivate you and how you sought to resolve that.
Yeah, it's a good question, and I think like this is. I'll give a very personal answer. It's not necessarily one that people can relate to, but
Sure.
yeah, I think part of grad school is just learning what research is, and so one thing that attracted me to TCS before is the ideas are very very elegant, and I like learning elegant things, and I like thinking about very nice things. I was learning a lot in grad school, but I was mostly solving individual problems. Like we would pick some research thing, and then we would study it, and then we would have some nice idea to solve it and connect it to other things. And it was nice in isolation. But after solving one thing or failing to solve one thing, I would move on to something else that's kind of completely unrelated. which is also interesting, and I would learn things from it. But basically, I was sitting at solving problems in isolation, and the problems themselves were not very connected, and I would enjoy the process each time, and I would learn a lot from it. But there wasn't something deeply driving me in terms of like these problems are important to solve, and this is why I care about them. There was also part of an aspect. I also partly felt like a lot of like some of the things I was doing wasn't very fundamental. Like it was sort of building off of things that people had done and using interesting tools, but not really the fundamental work. And there were people doing the fundamental work, but I wasn't at the time like suited to do that kind of work. That's also something that drew me to ML. That a lot of the kind of work that needed to be done was very foundational. Like we didn't even like in a lot of fields that are more mature, at least the questions are established. Like people agree what the central questions of the field are, and they have some notion of what it would mean to solve those questions, to resolve those questions. But in ML, like even that is open. Like just even it's open to even ask interesting questions. And I think this
Hmm.
level of like foundational work is like something that drew me.
I see what you're saying. That actually, if you don't mind my jumping in for a moment, that
Yeah,
does remind me of a sort of dichotomy that one researcher I talked to spoke about, which I think kind of maps onto the way you're thinking about this right now. In that there's definitely two pretty distinct types of research. One in which, as you said, you were doing in TCS, where you're very focused on solving specific sets of problems, a lot of problem solving there, a lot of low level thinking. And then on the other side, you have this more foundational aspect of I'm a researcher who's going to try to formulate what are the important questions here and really just lay out the land that then gets cultivated by researchers down the line. Do you
right.
do you feel like that's more or less maybe an accurate dichotomy and you were kind of thinking along that?
Yeah, definitely. I mean, I really like doing the latter kind of work. But just to clarify, like there are people in TCS that are doing this kind of work. They're doing this kind of foundational work. I wasn't at the time, and I
Mhm.
didn't see a path towards me doing that. Like I was sort of missing that in myself, and I
Mhm.
wanted to find a field where I could do that, and I could feel motivated to do that.
Mhm. Yeah, I can see that being the case. I guess maybe what sticks out to me is in TCS, a lot of problems that one might work on have been thought about for decades. And
Yeah, yeah,
coming into deep learning, especially on the theoretical side of things, it's just such a nascent field. And so people haven't really set about figuring out how to formalize many of the things that you work on, for example.
right. Yeah, I will say that I am very glad I had that TCS experience. I think like the fact that TCS is such a mature field, it taught me what a mature field looks like, and like it gave me ambitions for what ML could look like in the future. You know, there is hope of having really nice unifying abstractions and having the right way to think about concepts. And yeah, theorists have put a lot of effort into coming up with the right definitions for things, right? Like the
Mhm.
Turing machine or one-way functions in cryptography, and these are the kinds of like definitions that I'd like to these are the kinds of objects that I'd like to abstract in ML.
Yeah, I'm sure there's a lot that the deep learning research community can probably learn from that more established field. I know that, as you said, having really good definitions of things is something super important. I often hear this criticism, especially in fields like AI fairness, for example, where there's just a proliferation of different definitions and people can't really seem to agree on a very specific set of things and get out a coherent research agenda. Maybe before we move on from here, you mentioned a couple of things that the deep learning community could maybe learn from TCS. Are there any aspects of the TCS community or research in TCS that you'd maybe like the deep learning research community to avoid?
To avoid. Oh,
Hmm.
oh, interesting. Yeah, yeah. I mean, definitely, of course. I think the TCS community naturally, as they should, like puts very heavy weight on mathematical proofs as the only form
Hmm.
of evidence for statements. Right? But as
Hmm.
soon as you start talking about objects for which proofs are just going to be intractable, objects that you don't even have formal definitions of, I think you have to be okay with making a bit informal statements with other forms of evidence, experimental evidence. And I think this is really the only way to make progress. Like instead of sort of giving up and saying mathematical proofs or nothing, there are intermediate stages of understanding that are less formal than mathematical proofs, but that still tell us something about the world. So I think sort of just being aware of the entire spectrum of different forms of evidence we can have and different levels of formality we can have about statements is good. Like I think also not being too restrictive about the types of scientific work, like the valid type of modes of scientific work in deep learning. Like you can do scientific work in deep learning that involves proving a theorem. You can also do scientific work that only involves experiments, and both are valid methods, and they'll let you talk about different kinds of objects. There's different like these each mode can let you do something different that the other mode will not let you do. I can elaborate on that too,
Sure.
but yeah.
Yeah, that makes a lot of sense. I guess in the world of theory and mathematical proof, for example, things can be really nice and elegant if you make them, but often that tends to require maybe a lot of assumptions that don't hold in actual practice. And so empirics can certainly reveal really interesting things that maybe theory can't describe quite as well, or just things that don't fit very well in theory. And we've seen that over and over again in deep learning. And what you're saying also, I think, speaks to a number of complaints I've heard about the process of submitting papers to deep learning conferences. I've experienced this a little bit myself. And then also reading papers where people are like, there's definitely this expectation of grounding your statements and all these levels of mathematical proof and abstraction. And that makes it maybe a lot more difficult to grok and understand than it has to be.
Yeah, yeah, definitely. I used to be a lot more frustrated with this in the past than I am now.
Hmm.
Partly because, yeah, when I was in grad school, especially in early grad school, a lot of things depend on whether your papers get in. Like your whole, your career can depend on it. And so I was very frustrated. We get reviews that like try to, you don't consider the whole story. I think over time I've become less frustrated, partly because I do think it's actually more of a reviewing problem. I think a lot of people in the community do actually respect this kind of work. At least from personal experience, I've had very good interactions with my peers and with people, and I think it will change in the future. But yeah, I agree. It's currently a problem, and reviewing incentives, yeah, tend to skew the kinds of things that people work on. Um, I'm hoping we can push back on that given time, but
Hmm. Yeah, I suppose that's just to be expected. So, in the line of work that I was hoping to discuss today, and I think I like the way that your thesis kind of titles this. One of the main objects of interest for you is an empirical theory of deep learning. I'm wondering if you can maybe explain what you would define an empirical theory of deep learning as.
right, yeah. So the way I described it in the thesis is I want to study deep learning as an object of nature, like an object in the natural world. So imagine we have this object which we call deep learning. It accepts some inputs. So the inputs to the deep learning system are everything that the user needs to specify. So things like the model architecture, the training optimizer, the data set that we train on, the exact training procedure, the activation function, all of the design choices in deep learning. This is the input to the system. And then the output of the system is the trained model. So this, and there's different ways to look at the trained model. You can look at it as just an input-output function. You can look at the parameters. You can look at the representations induced by the parameters. But whatever, this is the system as a black box. It takes in these inputs, which are all the design choices, and it spits out some output, which is the trained model.
Hmm.
And now my claim is we want to understand this system. And what I mean by understand is the process the process of deep learning defines a map from inputs to outputs, right? From design choices to the trained model.
Hmm.
And I claim we want to understand structure. Understanding deep learning means understanding the structure of this map. Specifically identifying stronger and stronger forms of structure on this map. So one form of structure, like for example, the line of works on scaling laws, looks at if we change one of the parameters in the input, the data set size, and we measure a single scalar of the output, the loss, how does this one parameter change the scaling of the loss? Right? So this is one form of structure about this map. But in general, this is like the broad picture. Like this map is not a random function. Like it's not a random system. It's not the case that if you change the inputs by a bit, the output will be something completely unrelated. But the process of training a deep learning method has a lot of structure, and I think of my research program in general as identifying stronger and stronger forms of structure here. You can think of this as like similar to just understanding any behavior, any like object in the world, right? You have some physical system that you can play with its input parameters, and you observe some behavior, and you want to see how does your inputs affect the output.
That's really interesting. And I guess one thing that maybe this kind of reminds me of is in the line of this whole maybe empiricism versus idealism readings in general. So I know that there are a number of theories that maybe attempt to characterize what sort of abstract object is a deep learning system. So if you look at like the information bottleneck theory, maybe it's trying to develop this kind of form of how a deep learning system is supposed to behave in and of itself, right? What is the behavior of these systems maybe independent of or possibly depending on how humans interact with them. And that kind of speaks to something like, this very abstract platonic form of like, what is a deep learning system? And the way you're looking at it is very specifically empirically, how can machine learning engineers, research scientists intervene on aspects of a deep learning system and then observe the resulting outputs as a trained model, as artifacts of a trained model that I can empirically observe?
That's right, but I would say actually, I'm interested more generally in the question of I would like to make as general statements about deep learning systems as possible. Ideally, even statements that don't require humans to define. So for example, like one question I'm interested in is even just defining this object of deep learning. I don't think there's a good definition of deep learning. You want a definition that includes everything that people currently consider deep learning, but which will also last into the future, right? Like 20 years from now, whatever people consider deep learning, if it's a natural evolution of this object, we should also consider deep learning. So it's not enough to say like deep learning is this set of ConvNets, MLPs, transformers, or this specific architecture. It's not enough to say that it's deep learning is just an arbitrary architecture that we train differentially, because arbitrary architectures can encode Turing machines, and that's now not specific to deep learning. But right, so I think there are aspects of deep learning that teach us something more general about learning, and not just about specifically how humans have been doing learning, or like how humans have been implementing these learning systems. Yeah, one question I have, for example, is I think this is a good question of how much of what is currently being done in deep learning is because of human constraints and the current state of human society, right? Like, for example, is deep learning sort of the optimal learning system in some information theoretic sense, or is it just a particularly good system given the hardware constraints that we have now, or given the compute or like monetary constraints that we have now, or is there some sense in which even with infinite compute, there's some like deep learning is a sample efficient learner? Yeah, so one way of phrasing this question is there's three fundamental resources in learning. Right? There's time, space, and samples. And learning is an interesting. So in the real world, we're constrained on all three of them. We're constrained on learning time, on memory, and on the sample size that we have. And in this particular under these particular constraints, we've developed a deep learning as a thing that works well under these constraints. But what would happen if we relaxed some of these constraints? Right? If we had, you say, infinite time and infinite compute, but limited samples, would we still use deep learning? Well, like if there was an alien world that where they didn't have these restrictions, would they still have developed something that looks like deep learning, or would they develop completely other, some completely other types of learning systems? Like the reason I'm interested in this question is because, yeah, like we don't understand how exactly why deep learning is working, but it might not be deep learning might not be the right object to study. Right? There might be something underlying why deep learning is working that if we can extract that out, that will tell us more generally that this entire other set of things is actually good to actually will work for us. Asking these kinds of questions of what types of learning system, or asking the question of what set of constraints led us to develop deep learning, and would we have developed other learning systems under different sets of constraints? Is one.
Mm-hmm.
So this was like maybe not completely related to your question.
Even then, I think that's a really interesting set of counterfactuals to look at. And I guess one example that maybe isn't straying too far away from the technical aspects of this would be things like the hardware lottery. And you already kind of referenced this, right? The idea that there's this back and forth influence between the learning algorithms we develop and the hardware we have. So, for example, transformers being an artifact of that desire to exploit massive parallelization in the way we design things, like multi-head self-attention. So I can definitely see that being a very interesting question to pursue. I have a hard time thinking beyond the realm of like hardware lottery style patterns, what that looks like. I suppose you mentioned maybe broader abstract aspects of like human society and how that maybe figures into the way these systems could possibly get designed. It's interesting to me, but I also have a very hard time thinking beyond some of these more technical aspects what it looks like to engage in thinking about those counterfactuals.
Right. Specifically, I was thinking even just of the technical aspect of this question of, like for example, my deep bootstrap paper. Part of this, which we can get into more, but it relates to the real world where we have sample constraints to this ideal world where we have no sample constraints, but we still have time
Right.
constraints. And this thinking about sort of this counterfactual is part of what led to that paper.
Mm-hmm. Yeah. So let's actually get into a couple of the papers. And before we get to Deep Bootstrap, let's first talk about your Deep Double Descent paper. I think that this is a really important and interesting paper. I hope that our listeners would be aware of the results, but let's maybe assume that they aren't and just start with what is the double descent phenomenon and what do you think are the most important claims in this paper that you'd like somebody to take away?
Okay, yeah. So the double descent phenomenon. This was first coined double descent in this paper by Misha Belkin and others. And the coined this phenomenon to describe. So there's a couple types of double descent, and the phenomenon was first described as model-wise double descent. And so here, what they're looking at is how does the test performance of a model change as you vary the size of the model. And this is interesting because classically, both from statistics and sort of learning theory, you might expect that you get a U-shaped kind of behavior where small models perform poorly because they're not even able to represent the ground truth. And then as you increase your model size, you hit some sweet spot where the models are expressive enough to represent the truth, and also you have enough samples to actually learn them. And then you might expect that as you increase the model size even further, your models become too expressive, and they're able to express sort of any function on your training data, and so you could overfit to your training data, and you could learn essentially a random function. So classically, you might expect this kind of U shape. So now the question is, okay, but what actually happens when you apply these modern learning methods to real data sets? And you do see this U shape in the beginning, but the point is that that if you then increase your model size beyond the point when it's expressive enough to fit your training data, you can see the second descent where the test error goes down again as you continue to increase your model size. And so now the question is, okay, how should we be thinking about this behavior? Because it doesn't follow from classical predictions of classical intuitions of how test behavior should vary with model size. So this is the model-wise double descent. What we did in our paper was we sort of generalized this, and we said this happens not only for simple networks, it happens for many modern networks, even on like large vision tasks. But also we observed another kind of double descent, which is over training time. So you can take the same model, and as you increase the number of train steps, you'll see a double descent over training time. And the general claim is that these are all instances of the same sort of general behavior, which is as you increase the effective capacity of the model. So basically, the true x-axis should be the effective capacity of the model, and the general double descent claim is that you often see a double descent in test performance as a function of effective model capacity. And so how do we define effective model capacity? I think this is also an interesting aspect of the paper. That so we now want to define some natural notion of model capacity that captures both increasing model size and increasing train time. The point is that a super large model that's only been trained for a few steps should effectively be like a small model because it's been undertrained. So how do we capture this? We had this notion of effective model complexity, which is this is by the way, I really like this definition. So the definition is you have some black box training algorithm. Or I should say, like a lot of my research, I try to have definitions that abstract away as many pieces of the process as possible. So this is one instance of that. So we consider like a general training algorithm to be a black box that inputs some set of samples and outputs a model. Okay, and now we can consider the effective capacity of this black box as the maximum number of training samples for which the model that is output can fit that train set. Okay, so now you can increase the capacity of this box in many ways. You could increase, so this box will encapsulate the entire process of instantiating a model, training it on the samples, and then outputting the model. Right? And you can increase the capacity in many ways. You can increase it by increasing the size of the network, or you can increase it by just increasing the number of time steps that the box trains on. Right? Or you could even increase it by, say, reducing the regularization parameter or something like that. So this is like a generic notion of for any training algorithm. It doesn't even need to be SGD. It doesn't even need to be neural networks, right? So any generic training algorithm, this is a way to define model capacity. And then our claim is that you'll see this double descent peak at roughly the point when the model capacity is equal to the number of samples. So that is when you're training on just barely the number of samples that your algorithm is able to fit. That's sort of when the algorithm is most sensitive. So one other reason I like this definition is because the units match. Like so previously we used to think of the double descent peak as when the number of parameters is equal to the number of samples. There's a couple of problems with this. First, number of parameters is not an intrinsic notion of model capacity, right? Because you can reparameterize your model, change the number of parameters, but not change the dynamics. And the second is that the units don't match. So it's nice that, like, definition, the unit of model capacity is itself samples, like number of samples that you can fit. So, okay, that's a summary of the double descent.
Yeah, I really liked your effective model complexity definition. And it actually, the first time I read it, it was very familiar to me, I think, because during my undergrad, I did some research that involved statistical learning theory, and I was playing around with a very similar definition I tried to develop of model complexity. I didn't quite get to a point where I thought about it in as abstract a way as yours, but I was trying to maybe bring in some more classical notions of complexity in a more concrete way. So I think my definition was something very similar to yours of like, the maximum number of samples. But then I was looking at, okay, what is maybe the Rademacher complexity of my model? And so I think I defined it as something like the maximum number of training samples where you can achieve 0 or like smaller than epsilon Rademacher complexity. And yeah, I really liked yours because I thought that the training procedure aspect of it, especially when it comes to deep learning and tying this to the empirics of how these models work, was really fascinating. So you mentioned a couple aspects of training procedure by which we can increase a model's complexity, like varying the regularization, varying the number of time steps, varying the model itself. And I imagine this also incorporates perhaps differing things like the optimizer, the learning rate schedule, incorporating early stopping, things like that, right?
Mm-hmm. Mm-hmm. Yeah, yeah, and so this is like a very ambitious conjecture, right? And because it encapsulates a lot of things. We tried to test a bunch of things in the paper. There are many things untested. It might hold for some of them. It might not hold for some of the others. But yeah, I think I like this sort of way of this style of research of sort of trying to phrase the most general possible conjecture, like make some observations, try to phrase the most general possible conjecture that encapsulates those observations, and then go and try to test this conjecture as you can.
Mm-hmm. Yeah. So one thing that sticks out to me as we think about this definition and the various parameters of the training procedure you can tweak is this not really dichotomy, but scale we spoke of things that you can describe with very formal mathematical ideas versus things that come out in empirics. And one of those is something you explored in the paper with epoch-wise double descent versus model-wise of as I take maybe a single facet of my training procedure and try to ablate its effect on the eventual model complexity, what does that look like? And of course, you can do that with more than just parameters and number of epochs I train for, but you can do this with the optimizer I use, maybe early stopping, as I think you explored as well, or learning rate schedules. And do you think that maybe these ablations are just aspects of the training procedure and have effects that have to be explored empirically? Or do you think that there are ways to incorporate that a little bit more into things that you can describe mathematically with a more theoretical bent?
Yeah, I think there's definitely ways to do both styles of research. One way I like to think of these different styles, so top down and bottom up research. Where top down research is where you start with the object that you care about describing. In this case, it's the actual deep learning system in the wild, and you try to simplify that object down to the statements that you sort of abstract away complexities of this object until you can make a statement cleanly that you can then test empirically. Mm-hmm. And that's the style of research I usually do, but it's complemented by this bottom-up style of research where you start with mathematical objects that you can formally understand, but that are much simpler than the real world. And then you try to build up the complexity of these mathematical objects to better approximate behaviors that you observe in the real world. And I think these both things are complementary. And this has actually happened. It was really nice to see this happening in the double descent line of work, where after our paper and after other papers, there have been a lot of theoretical works on better understanding aspects of overparameterization, better understanding epoch-wise and model-wise double descent in simpler theoretical models. And it's not like, so the simple models have the disadvantage that they're not the actual thing we care about, but the advantage that they're simple enough to study in complete depth and sort of theoretically understand all aspects of the picture. So I think it has been actually very insightful to see sort of this theoretical development alongside the empirical work.
Mm-hmm. Yeah, I do like that a lot of the theoretical developments followed out of this work, because I think that this double descent phenomenon, as you mentioned, came out of that Belkin paper. It was something we were starting to observe, and it just seemed wild at the time. So it's nice to see people looking into the various things we can tinker with and what happens there. One thing I want to touch on in this paper is maybe your intuitions about why things like model-wise double descent actually occur. I think you touch on them a
Mhm.
little bit in the paper, and I would think that part of this maybe relates to what's happening in an optimization procedure like SGD.
Right. Yeah. So I think the sort of theoretical developments here actually give a lot of insight. So you can get double descent even for linear regression, just standard linear regression, as you either change the number of features or you vary the number of samples.
Mm-hmm.
Actually, I have a simple note on this for varying number of samples. But what happens there is that the optimizer becomes extremely sensitive to the input data at the point when the number of parameters is equal to the number of samples. Like in linear regression, right? When you have number of samples that's exactly equal to the dimensionality of your data, then this design matrix just becomes poorly conditioned, meaning that like changing one of your data points will completely change your solution. And so if you have this behavior, if you have a very sensitive optimization procedure and you have noise in your data, which any kind of real data will have some small amount of noise, then these two things are what gives you catastrophic behavior at this interpolation point. And I think this intuition from the linear regression is actually very close to what's happening. It's like probably very close to what's happening in these neural network cases too, where when the model capacity is exactly equal to the number of samples, then there's essentially like only one model that will fit your data. And so if you change the data by a little bit, it becomes like the model that you produce becomes very sensitive to the particular choice of data. And so fitting your noisy data will behave catastrophically. This is sort of whereas if you're away from this point, if you have a lot of model capacity, then the model is expressive enough to be able to fit the noisy data non-catastrophically. So it has enough capacity to fit the noise without completely blowing up its solution. Actually, we have a follow-up paper that should be coming out soon with Misha Belkin and Neil and Jamie and others at UCSD and Berkeley that I think sort of tries to clarify this a bit. It says there's three kinds of overfitting behavior that you can observe. You can have benign overfitting, where asymptotically noise does not hurt your model. This is sort of the optimal kind of learning procedure. Then you can have catastrophic overfitting, where the noise completely like destroys your solution, which is what happens at the double descent peak, where any small amount of noise will just completely throw your model off. Or you can have what we call tempered overfitting, which is where the noise does harm you, but it harms you in bounded ways. So the noise will sort of only harm intuitively some like local neighborhood around the noisy points. It won't destroy the whole solution.
Interesting. So that last notion sounds like there's a sort of robustness going on where the maybe noise introduced or something like a single sample point, as you said, isn't destroying the network completely, but this local area, is it maybe aspects of where the network is in regards to like the under parameterized regime, interpolating regime, over parameterized regime, where this has its effect?
Yeah, definitely. So in the under-parameterized regime, if you have enough samples asymptotically, then you will be able to filter out the noise. Like the
Sure.
under-parameterized models will overfit benignly, but over-parameterized models, yeah, is where we get this tempered overfitting behavior. By the way, this was inspired partly by our distributional generalization paper as well, where that was where we observed this behavior that sort of adding noise has this bounded but constant effect.
I see. So, with regards to this whole idea of more or less picking the right model in this process of double descent, I think one way you
Mm-hmm.
articulated in the paper was that SGD is basically able to find the model that fits the train set. So that memorizes noise, but also performs well in the distribution. And
Right.
there's been some further commentary on your paper. So one of my former lab mates from school, Evan Hubinger, wrote a link post to your double descent paper. And one thing that was really interesting that I was hoping to get your comments on that he discussed was this idea of inductive biases sticking around. So he said that he thinks double descent does this really good job of showing why all of the performance gains you get past this interpolation threshold, where your model complexity roughly is equal to the number of samples, comes from your implicit prior, where by implicit prior, he means the model architecture and the choice to train with something like SGD. I'm curious if that kind of reflects your own intuitions on what's going on there, and if you have any thoughts on the role of inductive biases in this whole process.
Yeah, it's definitely correct that everything that happens past the interpolation point strongly depends on the inductive bias, and the fact that learning is working in that regime at all means that you have a good inductive bias. Uh, I think the theoretical works on double descent also back up this point. So you can look at random Fourier feature models, for example, where growing the model size means growing the number of Fourier features. And there you have a very nice interpretation of what happens as you grow the model size. It's essentially you get a better and better approximation of the true infinite object, where the infinite object is just the kernel, like the Gaussian kernel. And so then the fact that learning works requires that learning works for the Gaussian kernel, which is a statement about the implicit bias of this kernel regression for your problem. So yeah, I think I definitely agree with that. I think a question is like, how do we characterize inductive biases? What is sort of sufficient? What do we need to know about the architecture and the optimizer to evaluate its inductive bias on the given data distribution? Yeah, I think that's very. I think like our deep bootstrap paper also relates to that. It sort of says that you can understand offline inductive biases through online inductive biases.
Interesting. How about we move on to that deep bootstrap paper then? So
Yeah.
let's hold the inductive bias discussion for a second, and maybe first just start with the TLDR of this paper.
Okay. Yeah. So the TLDR of this paper is that in a lot of supervised learning settings, where we train for multiple epochs and we reuse the samples from many epochs, and if our models are big enough, we'll continue using the samples until we've completely fit the train set, right? And we typically see test performance improving as we do multiple epochs. And the TLDR of the deep bootstrap paper is, let's imagine some ideal world where we actually had infinite samples from the data distribution that we cared about. So you could just hit. If you cared about ImageNet, you could just hit a button and get a million more samples, million fresh samples from the ImageNet distribution. Now the claim is that if you were in this world, you would never repeat samples. You would just continue training on the stream of samples. And the claim of the deep bootstrap is that your model in this world will perform very similarly to your actual model. In that, basically reusing, having access to fresh samples doesn't actually help you that much compared to reusing samples. So intuitively, this is sort of saying that reusing samples doesn't harm you much. You might think that that reusing samples can cause you overfitting or things like that, but our claim is that empirically, reused samples are almost as good as fresh samples. And so the message of this paper is that to think about generalization. So when we fit to a finite train set, we think of this as a generalization problem, right? Like all models can fit the data, but we want to use models that generalize well to test data. But if we then pass to this ideal world where we just have infinite data, then it's a pure optimization question. There's no generalization question anymore. We just want to be using models which optimize well on the data sets. And so the message of this paper is that it might be possible to understand generalization just by understanding optimization, which we might hope is a much simpler, like more tractable thing to study.
Interesting. So before we jump into some of those broader claims here, one thing that sticks out is this idea of real world performance where you are reusing samples being similar to the ideal world. And you said in particular that reusing samples poses no harm. One thing I wonder there is, and I think you maybe explore this a little bit, but whether there's, a threshold, right, where this actually
Oh
occurs.
yeah.
Because one of those assumptions we always make in these statements is that my training samples are going to be representative of my data generating distribution, right? And then just statistically, a larger sample is going to more closely reflect what that distribution actually looks like and gives me more to learn with. So could you comment on that part?
Yeah, definitely. So I claim that this holds even for small sizes of train sets, but that this only holds up to the point. So how long can you expect this to hold for? I claim this only holds up to a certain time, right? And I claim it holds up to the time when you fit your train set in the real world. And this is sort of the longest you can hope for it to hold until, because once you fit the train set, then doing more epochs isn't really going to help you that much in the real world, but it'll always help you in the like training for longer will always help you in the ideal world, because you see fresh samples, you will always continue to improve. So I claim that this approximately holds up until the point when you fit the real world train set. But interestingly, I claim this holds even for small. I don't only claim this holds for large enough sample sizes. I claim it holds even for small sample sizes. So even if you have very few samples, um, you will behave as if you were seeing fresh samples until your optimizer stops moving, as in until you fit the train set, and that will happen sooner for a few samples than it will for most samples.
Right. Yeah, that makes a lot of sense. And I guess that there are relations to the whole overfitting discussion we've had before there. One thing I noted in your paper was you seem to restrict your claim, this bootstrap error bound, the relation between the real and ideal world, to be about deep learning for supervised image classification. I was
Yeah, yeah.
wondering, yeah, what resulted in that choice to the restriction?
Yeah. I mean, if you ask me I actually believe this claim. I would like to make this claim for much broader family of models. I mean, and I think it likely holds for a much broader family of models. We made the claim very carefully to be like so that we could make a claim that we had sufficient evidence for. Um, Basically, for sort of paper review reasons, right? Like, I actually believe this claim is much more general, but that was the level of evidence that we had. It was the strongest claim that we could make with a large body of evidence to support it. Yeah,
Hmm.
but yeah, I actually believe it's much more general than that. I I think I even think it holds beyond deep learning. Like, I think it sort of holds for any sort of reasonable online optimizer. Like, the claim makes sense to phrase for any online optimizer, even beyond SGD on deep networks. And I think it's probably true for some much more general class of online optimizers. Not all online optimizers, but some more general class.
Hmm.
But I don't know exactly, like, so I think the claim is much more general than what we said, but I don't know exactly the more general form for which it should be stated. So that's why, yeah.
Hmm. That makes sense to me. Yeah, and it's definitely a good place to start, I guess, to couch it and where you do have that sort of evidence. Towards the end of the paper, you have this section where you describe a couple of different deep phenomena through this bootstrap lens. And I think maybe some of our earlier discussion will come back into play here. But from that section, you discuss a couple of things, like that it's surprising the same architectures do well in over and under parameterized regimes, that there's some close relation of different phenomena. Like if the bootstrap error is small, we should expect architectures that optimize well in the ideal world or infinite data regime also optimize well in the over parameterized regime. Some things about implicit bias. What parts of this section would you most want a reader to take away?
Oh, yeah, interesting. Um, I think it is this thing about the same architectures working in the over and under parameterized regime. I think this is a priori something. That question is actually what led to this paper. Like, thinking about that question is what led to the experiments in this that eventually resulted in this paper. Because it is actually a priori very surprising that we use for image classification, right? Um, in the over for small image data sets like CFAR, we're in the over parameterized regime, right? And in the over parameterized regime, we can all any okay. So how do we do architecture? So let me first convince you or the audience or whatever that this is a surprising behavior, and then I will describe why the deep bootstrap can help explain this. So why is it surprising? Let's first consider the overparameterized regime. So here we have a small data set. And how do we do architecture selection in the overparameterized regime? Well, any model, any architecture that we pick, we can train it to fit the train set. So there's no optimization concern. Every model will have zero train error, like an MLP, a CNN, or whatever. So we need to pick an architecture that generalizes well, right? All the architectures can optimize on the train set. We just care about something that has a good generalization gap. Whereas, okay, now let's consider the effectively infinite data regime. Like, let's say we have billions of images, with Facebook or Instagram or whatever, and now we need to pick an architecture for a learning problem. Now there's no generalization problem because we have billions of samples. Every architecture will generalize. So what considerations do we have in picking architecture? Well, we have a finite amount of time and compute budget. Right, and we want to pick an architecture that will optimize quickly, given the amount of optimization steps that we have time for. And so there are very different considerations in both of these regimes. In one, we don't care about optimization sort of at all, because every architecture will fit the train set, and the other we only care about optimization. So it's really surprising that we use the same kind of convolutional nets in both of these regimes.
Yeah, I do agree that that's a really surprising finding. As you said, it's interesting that in these regimes where we are over-focused on optimization versus not caring about it at all. So I think as far as lessons there, one thing we were speaking about too was the inductive bias discussion we were having over in the previous paper. So before we move on to distributional generalization, can we maybe take a second just to rehash what you were beginning to say in terms of the relationship between those comments and this paper?
Right. Yeah. So I think the way you think about inductive bias is sometimes very different, depending on whether you're in the underparameterized or the overparameterized regime. Right? Like in the underparameterized regime, we have the classical tools for thinking about inductive biases in terms of learning speed. Whereas in the overparameterized regime, we think we need different tools. And part of the deep bootstrap message is by saying that we can use actually the same tools. So we can carry over some of the tools from the underparameterized regime to study the overparameterized regime. Because in the ideal world, everything is underparameterized. The models are never fitting the training data sets because there's just an infinite stream of data. And so we can study inductive bias there just as an optimization concern. And then if you believe the deep bootstrap, then we can put that online learning inductive bias into the offline generalization inductive bias.
I see. That sheds some really interesting light on, I guess, Evan's concern there in the overparameterized regime where that matters. And I can see how being convinced of this deep bootstrap thesis maybe provides further evidence for what he was saying there.
Oh yeah, I also think studying this ideal world regime is becoming more and more relevant these days, where we see these models just trained on these huge swaths of internet data, and they're actually underparameterized. So part of the deep bootstrap is saying if you study the ideal world, you will understand both these really large model settings as well as the old supervised small data settings.
That makes sense to me, I guess, especially for the work we're seeing out of industry. You mentioned training with photos off of Facebook or Instagram where there's billions of samples there. The ideal world is starting to sound less like the ideal world and a little bit more like our real world now.
Exactly. Yeah.
Yeah. So let's go ahead and talk a little bit about distributional generalization. And my first question on this paper isn't actually about the technical work. It's noted on your site that this paper has been rejected from quite a few conferences. You've submitted it quite a few times by this point. And I read some of the reviews there. The iClear 22 one makes it sound like you're a lot closer. But this feedback does seem pretty frustrating. Can you take some time to maybe relay your thoughts on the paper's novelty and how you feel about the feedback you've received on it so far?
Yeah. I mean, luckily now it's been enough time that I'm kind of calm about the feedback. But in grad school, it was very frustrating, actually.
Hmm.
Yeah, part of receiving feedback like this, like, made me almost want to completely leave academia at some point. I
Hmm.
got over that at the end. But yeah, this is the paper that I'm still most proud of, and definitely the thing I'm most proud of in grad school. It's a very non-standard paper. Like, I understand why it's been rejected. It makes complete sense. It's extremely non-standard paper. We don't take an existing problem and then study it. Right? We invent our own problem. We say, here's something. Let me convince you that this is a problem, and then let me try to solve it. And it's a very
Hmm.
non-standard thing. It has no application, well, no direct applications. There actually are now some sort of follow-ups, but we didn't we didn't claim has any applications, um, and we didn't prove any theorems. Well, we proved like one small theorem, but we didn't. It wasn't a primarily theoretical work, so it didn't like fit into any of those standard types of papers. And so I understand that it is a hard paper to review because there are not many papers that try to do something like this. But yeah, I think it's still the paper that I'm most proud of. It took a while. I think we really have some sort of nice ideas in it, and we I feel like we made some discoveries in this paper. Like, we made some observations that the empirical observations were surprising. Then we figured out how to capture those empirical observations in like this general conjecture, and then we tested that conjecture in settings that were completely outside the initial observations, and it still held. So yeah, I'm still excited about this sort of work.
As a scientific paper, I really liked it. And I do agree that it's a very meaty paper. I can also see from how you just articulated it why those rejections might have occurred. It is really hard to have this totally new problem and be like, okay, not only am I solving it, but I'm convincing you of its importance. And I suppose that
Right.
speaking to how proud you are of this, that's no small task. That's a really big thing to just stake out this entirely new problem and make an attempt to convince other people that it's worth taking a look at. Before we get into the definitions you present in this paper, we've touched on it, but let's first maybe define what generalization is in general and what some of the classical definitions are that you were thinking about as you approach this paper and how they might be lacking.
Right. Yeah. So classically, we think of generalization with respect to single scalars. And so we say there's one scalar that captures there's one scalar that captures performance. So this might be test loss or test error or some other kind of test metric, but it's always a scalar. And we say generalization is when this scalar has a similar value on its train set and on its test set. This is sort of the basic definition, and then the whole like a lot of generalization theory is when can you guarantee that this scalar will have similar values on train and test set. So this is the classical setup. A first observation is that like models are much more than just scalars, right? When you get a trained model, it defines an entire function from its input space to its output space. And so even if you know exactly how well this model generalizes in the classical sense, you know exactly its test error, its test loss, that actually tells you very little about the model. Like, let's say you have a model that's 95% accurate in terms of test accuracy. But there are many different models that are 95% accurate. That you don't know where this 5% of errors are and what's the distribution of that error as a function of the entire training procedure. And this is it's more than just error, right? Like, there are many if you have a multi-class classification problem, there are different kinds of errors. You might want to know both on which sets of inputs is it likely to make errors, and what kinds of errors does it make on those inputs. Like, in general, you could want to understand the entire function as a function and not just one scalar attribute of this function. And that was part of the motivation for this work, trying to understand more aspects, trying to understand generalizations in more than just scalars, like of the entire function.
Great. So with that motivation, how would you articulate your description of distributional generalization then.
Yeah, so distributional generalization, it proposes studying this object, which is okay. So we want to study this input-output behavior of this function, f that maps in inputs x to outputs y. How should we be dealing with this? And we claim that a core object is this joint distribution of inputs x and outputs f of x, where x is now drawn from the distribution of interest, so the train and the test distribution. This is already restrictive because you could care about the function of distribution, but we're simplifying one aspect of this just to be able to better understand it. So we're saying if we care about only on distribution performance, then we really just care about this joint distribution x f of x, and I want to now understand the structure of this joint distribution. This is now a joint distribution that's defined both on the train set and the test set. Looking at the joint distribution of inputs and outputs of the model on its train set and of inputs and outputs of the model on its test set. So if you know the test joint distribution exactly, then you know essentially everything about the model at test time. So you know its test error and things like that. You also know exactly where it makes the errors and what kinds of errors it makes.
And one thing you kind of mentioned in how this sort of came about, how you developed this idea of distributional generalization, was an observation that you noted. And from what I remember at the beginning of this paper, I think you talked about this observation on the CIFAR 10 data set. Can you tell me a little bit at a high level about what you observed there?
Yeah. So this was the experiment that when we had this experiment, we knew we had something. And then it took like 3 more months to figure out exactly what we had. So the experiment was the following. Let's say you were solving a binary version of CIFAR 10, where you're trying to classify things as objects or animals, just a binary classification problem.
Mm-hmm.
And you add a specific kind of label noise on the train set. So you just flip the label of cats from animals to objects with some 20% probability, some probability. Okay, and then you train an interpolating model on that train set, and you see what kind of errors does it make at test time. So you could imagine a number of things. You can imagine, okay, the label noise has kind of messed up the classes a little bit, and maybe you have sort of uniform noise on everything. It's a binary classification problem. Maybe you just sort of uniformly make some errors. What you actually see, though, is that it makes the exact same kinds of errors. So if you just flip the labels of cats on the train set, then your trained classifier is just going to misclassify cats. The other animals are going to be relatively untouched. So this is interesting for a number of reasons. So first, it's not the optimal behavior. The optimal thing to do is like the denoised version of this, but also because it's doing something local, right? You're only messing up the label of cats, but cats are just one subset within the larger class, right? Because it's just a binary classification problem. We never give the network the label cats, right? We only give it these binary labels. But we've added noise in this very local part of the space, and that local noise has actually shown up at test time as well. So there was a while, actually, the first couple of months of this project, we were trying to. So this is the exact same kind of behavior you would get with one nearest neighbors, right? One nearest neighbors would also have this effect that adding noise would have only a local effect, but an exactly a local effect. So we were trying for a while to like formalize this observation by connecting it to one nearest neighbors and like trying to uncover, like see if mechanistically there was something close to one nearest neighbors going on. We weren't able to make that mechanistic connection, but like it eventually led to these conjectures.
So the things I marked down there are, as you mentioned, there's this really interesting property where I am noising a particular class in CIFAR 10 using this binary classification, animal versus object, and my interpolating classifier, which is capable of pretty much memorizing all of the noise in a data set, is therefore able to take into account that noise as well. This reminds me of that template overfitting you mentioned earlier, where it was this localized aspect of the noise is only affecting my model's performance on this particular class as opposed to ruining everything else for it.
Right. Yeah, exactly. So the template overfitting paper, which will be coming out soon, builds on like built on distribution generalization in a certain direction.
One other thing that really interested me about this paper, and I think you started speaking about this, is this idea you have of distinguishable features and feature calibration. Could you maybe introduce that?
Yeah, definitely. So, okay, so a question, so previously in the previous experiment, our intuition was that noise was sort of localized, right? But now the question is, what is this definition? What's the right definition of the local neighborhood for which noise affects? And this is a very subtle question because the experiment that I just described, that works if you train a ResNet, right? Like if you train a very good network, you will get the behavior that I described. It will not happen if you train like a bad network, like an MLP or something like that. And that should make sense because an MLP can't be trained to distinguish cats from dogs, even if you trained it on this exact task. So it shouldn't behave differently on cats and dogs in this like weird, noisy label scenario, right? And so we want a conjecture that is general enough to capture both these behaviors. That will tell you like both when things happen and when they don't. And so intuitively, like the ResNet was powerful enough to localize things down to the level of cats and dogs, and even to maybe even to finer substructures, right? Like if we had label noised only black cats or something, or black cats who are like running outside, that might work as well for strong models, but it won't work for weaker models. Weaker models essentially have a coarser locality than stronger models intuitively.
Sure.
Right. So we wanted a definition that captures something like the finest level that classifiers can distinguish, the finest sort of partition that classifiers will be localized within, and that motivated the definition of distinguishable feature, which is essentially exactly this: that a distinguishable feature is a partition for which a classifier that is trained to classify parts in this partition will reach high accuracy on the exact same using the exact same number of samples and the exact same training procedure. So a distinguishable feature, it's a function of number of training samples, training distribution, and training procedure. And it says for given all three of these, it's a partition which can be classified well to high accuracy.
Yeah, maybe to make that a little bit more concrete with an example from your paper, I remember you looked at AlexNet trained on ImageNet, and one way you could think of that coarse to fine-grained idea of a feature is the class of dog, not dog, in versus being calibrated with respect to what are the different breeds of dogs that I might be able to classify. So maybe my network can classify this thing as a dog. This isn't a dog, but maybe it's incorrect when it tries to figure out specifically what breed of dog this thing is.
Yeah, exactly. Yeah, and I think it was interesting that we thought of this AlexNet experiment after we formulated the conjecture. Like our conjecture initially was meant only to capture the effect of label noise, right? The localized effect of label noise. But it turned out to capture even behaviors of networks on actual data without label noise. Like it can capture the fact that AlexNet, even though it's not a great network for the original task, it has high test error. Okay, here's a good example. AlexNet, like as you said, AlexNet has high test error on the original 1,000 class problem, but so it has, I think, like a roughly 40%, 30 to 40% error, but it's not making these errors arbitrarily. It actually sort of knows what a dog is. It will, if you feed in some image of a dog, it will output some other dog label with high probability, like 98 to 99% probability. So the errors are sort of, clustered within the dog class and the not dog class. This is an aspect of generalization that knowing just the test error will not tell you about, right? It's the finer structure of generalization, and our distributional generalization conjecture captures this. It says that you should expect this because the dog versus not dog is a distinguishable feature to AlexNet, meaning it could be trained to classify dogs versus not dogs. And so you should expect that even when it's trained on finer problems, it will respect this coarser structure.
Yeah, I can see how that idea of fine versus coarser structure and trying to understand these things in a more fine grained way than just, as you said, a single number, a single scalar is really beneficial. And I think also it speaks again to the importance of expanding our definition of generalization to encompass these things.
Mm-hmm.
Before we wrap up on distributional generalization, are there any other takeaways or notes from this paper that you think might be important just to mention?
Yeah, lots of things. Some of them are going to be in our follow in our template or fitting paper as well. But yeah, I think one interesting aspect of this is it again highlights a difference between the over-parameterized setting and the under-parameterized one. So in the under-parameterized setting, you will not get this behavior that you won't reproduce noise at test time. Like if you train on this exact same setting with an under-parameterized model, it will not reproduce the noise at test time. But and so in that sense, our conjectures give another distinction between behavior in the over-parameterized world and the under-parameterized world. But we do actually have a unified way of thinking of it. The unified way is that the general thing you should expect is that the behavior on the train set is close to the behavior on the test set in terms of their joint distributions. So in the over-parameterized world, models fit the noise in the train set, and so they reproduce that noise at test time. Under-parameterized models don't fit the noise at train time, and so they also don't, reproduce the noise at test time. So I think this is like a unified way also of thinking of why things like regularization and label smoothing can help with noisy data, because things that prevent you from fitting the noise. Yeah, here, like one takeaway is things that prevent you from fitting the noise at train time should also help you being hurt by noise at test time.
Yeah, I do like that characterization a lot. So before we get on to, I guess, some less technical things, we'll talk about a few of the tweets you have showcased on your website.
Okay, yeah.
This will be fun. Is there anything about your current work that you're doing that you'd like the audience to know about? So you mentioned the template overfitting paper, for example.
Yeah, so I'll just mention one direction that I'm getting more into now. I don't have any concrete, works here yet, but I think it's important. I think a lot of people, including myself, have in the past studied machine learning by studying the effect of architectures and of optimizers and of training procedures. I think there's a lot to be done on studying the effect of on studying the structure in data. Like nowadays, it seems like a lot of advances are actually happening because of the particular structures in the data that we train on. Right? These large language models are exhibiting interesting kinds of few-shot learning, other generalization behaviors that are somehow driven by the data sets that they're trained on. But we have very few tools to describe the structure of these data sets. So I would like to. I'm currently sort of trying to think more about how to approach this problem. How can we sort of formally quantify the structures in the training sets, and can we better understand what structures in the training sets are being learned and producing these kinds of behaviors?
That's interesting and even surprising, I suppose, given the heavy emphasis that's placed on ideas like recently data-centric machine learning and the idea in data science that so much of your time is spent scrubbing and forming this qualitative understanding of your data, as opposed to, if you're a data scientist or ML engineer spending most of your time on architectures or models. It's interesting. But I do suppose at the same time, for maybe a theorist or a research scientist in deep learning, it is the models that are starting to exhibit crazy behavior or have done so over the past couple of years. And so it's maybe just following, as you were sort of pointing to, what exactly seems to be producing a lot of the benefits we're seeing. So now we're seeing applications of this same transformer architecture, but just maybe training it on a stupid amount of data or exploring the impact of scaling laws along various dimensions, or as you said, just varying the data and observing those behaviors. One paper I noted that came out a while back, I don't know if there's been further work on that front, was from Abu Mustafa at Caltech that was exploring this idea of data set complexity. I don't know that they were looking at anything about inherent structure, but I remember they were trying to characterize something equivalent to the idea of the Kolmogorov complexity of a data set. And I think that speaks maybe a little bit to the structure, or at least the information contained in the data set. So I was curious if you're thinking about we're starting to think about this from an information theoretic perspective as well.
Interesting. Yeah, I haven't seen this paper. Yeah, I'm very early stage in this process, so I'm not sure exactly what tools we want to use to describe these things. Definitely, information theoretic tools are one tool that we have. Yeah, it might even be that we need less mathematical and more empirical tools, right? Like maybe we want operational ways to measure structures in our data, even if we can't formally define exactly what the structure is.
Sure. Yeah, I can see that. So let's start wrapping up this interview with, I think, the fun part. On
Okay.
your website, you have a couple of different tweets showcased, and I wanna talk about a couple of the opinions in there. So one that I really liked was this idea of science for science's sake, and I have written down what you said there, that a scientific field should reflect on its intrinsic motivations and not become too distracted by the demands of technology. I'm curious what got you thinking about this and maybe how this applies to your work in deep learning and how you think about that more broadly.
Yeah, I think this is this was one thing that okay, so I think deep learning conference culture tends to shoehorn papers into either sort of application papers or pure theory papers. And I had observed that papers which do experiments but which don't prove theories, but which don't prove theorems, are sometimes not, like, their role is not understood. This is one thing. The other thing is I think a lot of papers themselves get confused in what their motivation is. Like I think it's it's almost distracting to if you care about technological development, it's almost distracting to try to do science as well. And if you care about the scientific understanding, it's often distracting to try to like claim your understanding produces some improvement. I think there's actually kind of a unfortunate trend that it's not the case. It's not the case that true understanding immediately results in improved applications. I think it's kind of very hot these days to like claim you have some understanding and then show that, oh, and so we can improve this system using our new theory or whatever. I understand like that this pressure is probably from reviewers where reviewers like really like to see some kind of deliverable from your understanding. But I think like just historically, science takes time, and scientific progress usually eventually results in improved technological applications, but you shouldn't expect it to happen immediately, and it doesn't necessarily need to happen by the same people. So I think I think just people like I really like to read papers that are focused, that they're clear about their motivations and they study that in the best way possible. And they don't sort of get distracted by looping in appendices or do this and that and like adding in some sections to prove some random theorems. Like it's a a a good engineering paper that improves an application and like is a very strong result stands alone without any theoretical understanding, and a good scientific paper that more deeply understands something but doesn't improve an application also stands alone. And I think these two types of things should be just respected on their own. And I think you can like do almost a lot better work by not trying to do everything at once, just trying to pick what you care about and do that very well.
That's really interesting, and I can see how that maybe confusion gets affected by incentives as well with regards to the
Yeah,
reviewing process. So
yeah,
this reminds me of one of the papers I worked in as an undergrad that ended up being pretty much a purely theory paper, but we were trying to, formalize these ideas of overfitting and underfitting and looking at information theoretic perspectives. And I had some ideas for experiments I wanted to run to see if, that could help us understand the phenomena here and if there was anything we could do with the relation between theory and empirics. And I planned to put in some appendices about the experiments we did and add those to the paper. But my advisor was like, why don't we actually just make this a theory paper? And I think in the end that was the right decision, because I think that made it a lot more focused and have a clear idea of what it wanted to achieve. But also, when we submitted it, some of the reviewers made a note that, hey, you don't have any experiments here. And I suppose that even in papers that lean theoretical, it seems like reviewers often tend to look for that sort of thing. So I can imagine that, especially when it comes to trying to make claims about things like deep learning, where the just even the idea of theory, you have this empirical aspect so tightly wrapped up in it, people might be a little bit motivated by what they expect reviewers to want as well as the focus of their paper.
Yeah, I think you're definitely right. Like, I don't blame authors for this as much as reviewers, because everyone acts according to the incentive, and everyone needs papers, right? Like people's careers
Mm-hmm.
depend on it. Um, yeah. By the way, I didn't mean to say that papers should either be purely experimental or purely theoretical. I think it's very good to
Sure.
try to use all tools that you have to understand the problem. One thing that I like to do though is, if or to one way I like to think about this is, if you have a purely theoretical paper and you want to and you want to introduce an experiment, describe what the purpose of the experiment is, and in what ways it is building on top of this, or in what ways it's complementing the theory, right? Like, you shouldn't have you don't have an experiment there for something that you've already proven, right? That's useless. So you have an experiment because you're studying some aspect that goes beyond the theory, right? Maybe you have the experiment because you actually have a more general claim and you've theoretically proved some special case of it, and now you're going to experimentally test some more general case of it, right? Or maybe you're testing the theorem in a slightly like different domain than the one you actually proved it for. And I like it when these kind of things are laid out. Of, we did some theory and now we're going to do some experiment. And here's exactly why we're doing this experiment and what it tells us beyond what we did in the theory. I think sometimes that aspect is missed. Of like, reviewers ask for experiments and then people just like include experiments in there, and it's not clear what the relation between the experiment and the theory is. But I think being very, explicit about what the relation is and why we're doing this is always good.
That makes a lot of sense, because it's like you're fundamentally with a paper trying to make a claim or a set of claims. And as you articulated pretty early in this conversation, there are different levels of formality at which you can make a claim. So you've got the very formal idea of mathematical proof, in which you can stake out something. And maybe that's a little bit restricted because you perhaps have to make assumptions for all the math to work out and things like that. But eventually you can get to this very rigorous, well formed, maybe even nice looking claim. But where experiment, of course, falls in there, it has to be, as you said, also kind of well formed and directed towards the claims you're actually trying to make. But perhaps it's, pointing towards a broader version of this more theoretical claim I've made. And I think that came across in a couple of the papers that you talked about, for example. There's also something that you noted. So the sort of broad thing you're talking about are how the goals of understanding and improving deep learning systems aren't really necessarily aligned. And
Mm-hmm.
this reminded me of a conversation I had with somebody else on this podcast, namely Greg Yang from Microsoft Research, whose work on tensor programs started out very theoretical, just as a way of trying to understand neural networks and their behavior, perhaps as they scaled in depth with other aspects. And eventually, after a couple of papers of this, they came up with this technique called new parameterization, which our listeners who have listened to that episode would be familiar with this. But broadly, it was this really interesting um, technique where, if you have a very large model, some flavor of GPT-3, you can actually shrink your model along maybe the width dimension, do all of your hyperparameter tuning on that smaller shrunk model. And it turns out the theory says those hyperparameters, the optimal ones you found for your smaller model, will also be optimal for your larger model because of the training dynamics. And this requires some small changes to the model, the way you compute attention, a couple of the different architectural choices, and of course is also only restricted. But it was really interesting to see this idea of something so useful, something that could really concretely improve our deep learning systems that also seemed to an extent well justified by theory. And when I spoke to Greg about the role of theory in deep learning, the way he articulated it to me, I think, has some overlaps with how you think about it, but was a little bit different in that he seemed to think that theory really should play this role of primarily trying to improve deep learning systems. And just that the role of a theorist, and I guess he thought that it was maybe a little bit misguided to pursue that goal of understanding for understanding's sake, and that the place where theory really best fit in with deep learning was where it could improve it. And I will say, I suppose that it took a while for tensor programs to become something that was concrete, practically useful. So I don't know if he would have been expressing that same opinion had that not happened and had tensor programs still been purely a theoretical framework. But I'm curious how you would think about and respond to that opinion.
Yeah, I think different people have different motivations, and everyone is justified to their and everyone has different styles of work, and I think both of the styles of work can be very productive towards different ends, right? In the same way that for example, mathematics is used a lot in engineering disciplines, as well as in scientific ones, and as well as just for mathematics' own sake, and the tools are useful for many different things. And so I think, yeah, and I know Greg from before. It's very nice that if he's interested in improving practical applications and he's able to do so with theory, then that's great. I'm actually not at all interested in improving practical applications, so that's why I don't even try. Like, really, like, I'm interested in deep learning because something is out there that we don't understand, and it's clearly like something big. Like, I think understanding it will teach us a lot, and so that's why I'm excited about understanding it. But yeah, I think, like, so personally, I don't work on applications mainly because I'm not actually interested in improving applications. But people who do can definitely make good use of theory. And,
Yeah. I think there's a lot of merits to both perspectives, and they both play really important roles. And you look at this in other scientific fields or mathematical fields as well. Like a lot of people, I'm sure, don't go into number theory because they think it's going to have applications. And for the longest time, it was pretty much pure mathematics, right? But then eventually, it turned out to have these applications to cryptography, and now we're seeing like abstract algebra have applications in post-quantum cryptography. And so I'm sure that there are now people working on both of those areas, some of whom have motivations that are purely about the beauty of the mathematics, and then others who are maybe more interested in the application side of it. And I think, as you said, that both of those are equally valid. I suppose the last thing I want to touch on before we close up here was another tweet you showcased on this topic of causally explaining generalization.
oh yeah,
And this touches on some of the things that we talked about earlier here, but maybe if you can give some context as to what that was about.
yeah. I think a lot of people. Okay, so the core confusion is people often don't think very clearly about what it means to understand generalization. Like, we're all trying to understand generalization, but what that means is very loosely defined. And and yeah, I had seen recently a lot of people saying things that certain things don't causally explain generalization. And okay, if you want to make a claim like that, you have to be very careful about what is the causal graph that you're talking about. Like, what would causally explaining generalization mean? And once you think clearly about that, a lot of these statements just don't make sense. Like, it doesn't make sense to say smoothness does not causally affect the generalization, because smoothness is not something you can intervene on. It's an observable. It's not a design choice. Like, there is no well-defined intervention for keeping everything the same, but just changing the smoothness. So anyway, I think basically just like thinking, if you're going to make a claim about something causally explaining or not explaining generalization, you should express your claim formally within a causal framework. Like, you should tell me what the causal DAG is, and then what are the variables you're intervening on, and what are you observing.
Yeah, that makes a lot of sense to me. I suppose that these aspects like smoothness, the like Hessians of whatever, deep learning system you're dealing with are interesting to study and maybe they do have interesting effects of the outputs, but as you said, those are not things we can like directly intervene on. And I think that there are some papers that do a good job of like studying these objects in and of themselves, right? Just as objects of interest to understand the behavior of the systems themselves, but then they're not making claims that like these are choices we can make. I think one that comes up was this paper, How Do Vision Transformers Work, where they studied things like the Hessian eigenvalues of vision transformers versus convnets and how that had impacts on the behavior that those two sorts of models had. And I thought that was really interesting, but of course, nowhere did they make the claim that these are design choices we can consider. It's like these are models we've trained, and then here are some empirical phenomena of the models that tell us something interesting.
Yeah, exactly. And I think that's fine. Like a lot of my work also makes statement. That's why initially I said it's about identifying structures in this input-output map, not necessarily like causal factorizations, but any kind of structure in the map. Like the deep bootstrap, for example, is not making a causal claim. It's just making this claim that the observationally this system can be well approximated by this one, up to any kind of like at the level of design choices. Not making any kind of causal factorization. Yeah, so I think it's very worthwhile doing a lot of these investigations, even if they're not sort of making causal claims.
Yeah, absolutely. So I think this is probably a good place to wrap up. Before we finish, if listeners are interested in maybe following your work, reading a little bit more of what we talked about, where would you have them go?
So my Twitter is usually pretty up to date on whatever I'm thinking about at the time. My website also stays up to date. Okay, so I think reading the introduction of my thesis is a good overview of my sort of research philosophy and my take on how I choose problems in deep learning and what kinds of things I'm interested in. The introduction and maybe the conclusion, which has a bunch of open questions, like vague open questions that I'm interested in, that sort of give us a taste of my research. And then for the more up to date stuff, my Twitter and my website are good.
Fantastic. I will make sure to include links to all of those in the show notes. And Preetum, thank you again for taking so much time to chat with me today.
Yeah, thanks a lot. It was really fun.
That's a wrap for this episode. Thank you so much for listening to this edition of the Gradient Podcast. You can find our podcasts, newsletter, and other articles from thegradient.pub and our Substack at thegradientpub.substack.com. If you liked the episode, please consider supporting us by sharing it with a friend or subscribing. And as always, we appreciate your ratings and feedback. See you in the next episode.